Okay, so this week we are talking about the greenhouse effect. So this is the key process behind climate change. So we have to understand the greenhouse effect to understand how climate change is working. And this is fundamentally about energy. It's about what happens to the sun's energy when it hits the earth. So hence the picture there, sun beaming energy down onto the earth. The greenhouse effect helps us understand what's going to happen with that energy. So in this lesson, we're going to explain the factors that make up the earth's energy balance, understand how greenhouse gases are warming our earth, and identify some of the human and natural causes of climate change. So, underlying all of this is the idea of the Earth having an energy budget where we're looking at energy coming in and energy going out. So, we have inflows and outflows of energy. And the Earth is an open system with respect to energy. So, unlike the carbon cycle, where all of that carbon would eventually come back around, we had a closed system, right? None of those arrows went off the page in your carbon cycle diagram. With respect to energy, we're an open system. Energy is coming into the earth and leaving the earth. And so any object that we have in our world that has a temperature greater than absolute zero is going to emit some energy. So there's going to be some sort of electromagnetic radiation coming off of any object that has a temperature greater than absolute zero. And the amount and type of energy that's going to be coming off is going to depend on that temperature. So the hotter something is, number one, the more total energy it's going to give off. So in the diagram there, you see a comparison between the Earth and the sun. And if you look at the height of those curves, you can see that the sun is emitting way more energy than the Earth. And in fact, the little note there shows they've scaled the sun's curve down by a factor of 10 to the negative 6. So it should be gigantic, way off the chart there, greater than the Earth curve, because the sun is a lot hotter than the Earth. And specifically, the sun is about 5,772 degrees Celsius, as compared to an average temperature on the Earth of about 13 degrees Celsius. So the sun's putting out a lot more total energy. The sun's also putting out its energy at a shorter wavelength. And this is a really crucial thing to keep in mind, is that energy that's radiated out from the sun is at a shorter wavelength. So it ends up mostly in the visible light spectrum. And that's why that part of the electromagnetic spectrum is what's visible to us. And our eyes evolved to be able to see the most common kind of radiation that we have bouncing around on our Earth. So that's why that's the visible part of the electromagnetic spectrum being the energy that is coming from the sun. The Earth's energy, in addition to being less total energy, is also being radiated out at longer wavelengths. So it's a different kind of energy. And so the energy coming off of the Earth is primarily in the infrared part of the spectrum. So we feel that as heat because our eyes aren't able to see infrared radiation that's that long of a wavelength. So we can feel it as heat. We can't see it the way we can see the shorter wavelength energy coming from the sun. And so the sun is radiating out that radiation in all directions, and some of it eventually hits the Earth. And we refer to that energy from the sun that arrives at the Earth as insolation. And that's just an abbreviation of incoming solar radiation. So energy coming to the Earth from the sun is insolation. And that's the source of all of the energy that drives our climate system. So let's take a moment to look at how insolation is affecting the Earth. So the sun, in addition to being a lot hotter than the Earth, is also a lot bigger than the Earth. And so the diameter of the sun is about 109 times as big as the diameter of the Earth. The sun is gigantic compared to the Earth. So as those rays of energy from the sun are coming to the Earth, we can treat them as being essentially parallel to each other. Right? They're not exactly parallel. They spread out slightly, but for all intents and purposes, the Earth is in such a narrow little band of the energy coming out of the sun that the rays are coming down more or less parallel to each other. The surface of the Earth, though, is curved, and it curves away from the sun at either end. So you can see here on this diagram, they've got it set up so the rays hitting the equator are hitting it kind of straight on, and then the Earth curves away from the sun towards the poles. And so what that means is that a ray of sunlight hitting the equator, hitting in the middle there, is coming down pretty much perpendicular, pretty much straight from above. And so it's going to be fairly concentrated when it hits the ground. So it's going to deliver a lot of energy per unit of area. So per, say, square meter, you got that light coming straight down, and so it's going to deliver a lot of energy to that square meter. But if you go towards the poles, where the Earth's surface is tilted away from the sun, so now the sun is going to be lower in the sky. It's not going to be directly overhead, it's going to be lower in the sky, and so those rays are coming in at a shallow angle, and so they're going to get spread out over more area. So instead of that, we have a 1 meter square sun ray coming down, instead of being fully concentrated on 1 meter square of ground, it's going to spread out over, 2 square meters, let's say, if we're at a particular point in that curve. So that means any 1 square meter of ground is only getting half of that ray. It's getting a lot less energy. The energy is less concentrated there. And it's that factor that explains why the equator tropical areas are generally much warmer than polar areas. Why it's cold at the North Pole and the South Pole, warm at the equator, is because the sunlight that you're getting at the equator is coming from more directly overhead, so the energy is much more concentrated as it hits the ground, whereas the energy from the sun that we get near the poles gets spread out because the Earth is tilted away from those solar rays at that point. So now this diagram shows the Earth kind of straight up and down here, but the Earth is only actually in that position twice a year at the days that we call the equinoxes, because the Earth's axis is tilted. The Earth's axis is tilted 23.5 degrees from being straight up and down relative to the plane of our orbit. And the tilt stays the same. We're pointed towards the same spot in the galaxy as we rotate around the sun. And so you can imagine the line of the Earth's axis, if you were to continue that imaginary line out, that line heads out towards the star we call Polaris from the North Pole, the so-called North Star. And so the North Pole continues to be pointed towards Polaris wherever we are in our orbit around the sun. So that means for half of the year, the northern hemisphere is tilted towards the sun. Because to go from the Earth to Polaris, you're going past the sun, we're tilted towards the sun. But then for the other half of the year, we get around to the other side of the sun. Now Polaris is kind of on the other side, so we're tilted away from the sun. And now the southern hemisphere is tilted towards the sun. All right, when you tilt the Earth, one hemisphere is leaning in towards the sun, the other is leaning away from the sun. And so when a hemisphere is tilted towards the sun, it's going to get more energy from the sun. It's going to get more insolation for 2 reasons. One is that the sun rays are going to be coming down more directly. The sun is going to be higher up in the sky. So those rays of solar energy aren't getting spread out over as much land, whereas in the hemisphere that's tilted away from the sun, those solar rays are getting spread out a lot, coming in at a shallow angle. And so you're getting less energy per unit of ground. Second, you're going to get longer days. So you have a longer portion of each 24 hours that you're receiving solar energy, right? So you're only receiving insolation during the day. But the days are going to be longer when you're in the hemisphere that's tilted towards the sun. You can see that on the diagram, that the line separating the half of the Earth that's getting sunlight from the half that's in darkness is not aligned with the Earth's axis. When we're tilted, the hemisphere that's tilted towards the sun is going to spend a larger percentage of its daily rotation in the illuminated half of the Earth. and a smaller percentage in the dark half, and then the opposite when your hemisphere is tilted away from the sun. You're going to spend a larger percentage of your rotation around the axis in the dark half and less in the light half. So when a hemisphere is tilted towards the sun, you're getting more direct overhead rays from the sun, and you're absorbing insolation for a longer percentage of the day because the day is longer than the night. And so that adds up to warmer temperatures. So whichever hemisphere is tilted towards the sun is going to have summer. The one that's tilted away is going to have winter. So summer and winter are opposite in the northern versus southern hemisphere. So I'm recording this in November, so we're moving into winter in the northern hemisphere. Meanwhile, the southern hemisphere is moving into summer. So that is what explains our seasons. Why does it get warm in the summer and cold in the winter? It is not because of the distance the Earth is from the sun. And in fact, the Earth is actually farther from the sun during the northern hemisphere summer. So that's the southern hemisphere winter. But here in the northern hemisphere, we're actually farther from the sun when it's warmest and cold, closer to the sun when it's colder. So it's not our distance from the sun, it's the effects of the tilt of the axis and how that changes the amount of insolation that we receive at different times of the year. So here we've got some insolation coming in from the sun. And when that energy hits the Earth, two different things might happen to it. So one thing that might happen is some of that energy is going to be reflected back into space. So it's going to bounce off the Earth and go back into space, still in the form of short wavelength visible spectrum light. And that's why we can see the Earth. If shortwave visible radiation wasn't bouncing off the Earth, then we wouldn't be able to see anything. The Earth would be completely black. Right? Black is the color that absorbs all of the light energy coming into it. So the fact that we can see the Earth means that some percentage of that insolation is getting reflected back off of the Earth and eventually out into space. But part of that energy is also being absorbed by the Earth. Whatever's not reflected is going to be absorbed by the Earth. It's going to raise the Earth's temperature because now the Earth has energy to increase the motion of the atoms and the molecules that make up the Earth. So we have a higher temperature, but then because we have a higher temperature, we're now going to radiate out our own energy. And as we said, since the Earth is much cooler than the sun, when we radiate energy out, it's going to be longer wavelength thermal radiation, infrared radiation. So you've got insolation, part of it gets reflected back into space, still in the form of short wavelength visible radiation. Some of it gets absorbed by the Earth and then re-radiated back out in the form of infrared or thermal radiation at that longer wavelength. And ultimately, those two outflows of energy should add up to the same as the inflow of radiation. Because if we're radiating out less energy, the Earth is going to heat up and it's going to start radiating more until we come back into balance, and vice versa. If we're radiating out too much, our temperature drops and that reduces our radiation out. So we've got this simple energy budget here. Radiation in, radiation out. So a key thing to be able to figure out when we're trying to understand this energy balance is, well, how much of that incoming radiation is being reflected, is not being absorbed, but is just bouncing back into space in the form of short wavelength visible light. And that's what we refer to as the albedo of the Earth. So albedo means the percentage of the insolation that's reflected back off the surface of the Earth, still in short wavelength visible light form. So just the percentage of that radiation that's reflected back is our albedo. You can think of it as kind of the shininess of the Earth. And on the little diagram there, you can see the range of albedos for some typical things on the surface of the Earth. And one thing you should notice pretty quickly is that lighter colors have higher albedos. So the lighter a color is, the more of that sunlight is being reflected off. So some of the highest albedo surfaces that we commonly find on our Earth are things like fresh snow. So fresh snow, of course, is white. And you may experience that albedo if you go outside on a day when it's sunny, but we have really fresh snow falling, and it hurts your eyes, right? There's so much of that light being reflected off the snow that you need some sunglasses or something to protect your eyes, because the albedo of that fresh snow is very high. It can be up into the 80s, right? So like 80% of the incoming light from the sun is being reflected back, right? So staring at some fresh snow on a sunny day is like 80% of staring directly into the sun. And hence you should wear sunglasses if you're going to be out in looking at that fresh snow when it's that bright. And then you see some other light-colored things with higher albedos too. So cumulus, stratus, altostratus, cirrus, those are all names of types of clouds. And we know clouds tend to be light-colored, right? Typical clouds are white. And so they're reflecting a lot of that solar energy back into space. And then as we go down, we find some things that are a little darker colors. Right? So we're getting sand and soil. Right? It's a little darker than snow. Then you go down and plants are darker than that. Right? So you see crops and savanna, and then things like forests, wet soil, and water have some of the lowest albedos. So open water, like in the ocean, very dark colored. And so it's absorbing most of that solar energy. It's reflecting very little of it back off the surface. So we have this range of albedos of different kinds of surfaces of our Earth based on what percentage of the insolation is getting reflected back off of them, back out into space in the form of short wavelength visible light. And so that means that one of the mechanisms by which we can change the climate is by changing the albedo of our land surface. So if we can change the albedo of the Earth on a big enough scale, then that will have an appreciable impact on our climate, because it will change what percentage of that incoming radiation is getting absorbed by the Earth and raising the Earth's temperature versus getting reflected back out into space. So in general, we see that low albedo urban surfaces, things like asphalt pavement, are going to be absorbing more energy than the natural surfaces that they might replace. So we talked earlier about the way that urbanization, right, going from like a forest to a shopping mall or something, changes the hydrology of that local area and changes its response to precipitation and the likelihood of flooding. We also see changes to climate as a result of urbanizing our land surfaces. If we take a forest and we replace it with pavement, make a parking lot or something, then we're going to absorb more of that energy. We're reflecting less of it, absorbing more of it. It's going to raise the temperature, and it creates something called the urban heat island. And this is something you may have noticed if you've ever gone from a very rural area to a very urban area on the same day when it's a warm day. You may notice that it seems hotter in the city. And that's that urban heat island, that the kind of surfaces that we have within an urban area tend to be lower albedo, absorbing more energy and raising the temperature more than a lot of the surfaces that we might have in a rural area. Okay, so if we know the albedo and we know the insolation, we can calculate what the temperature of the Earth should be. And we do this through this equation that I've got here that's called the Stefan-Boltzmann law. And you do not need to memorize this equation. I don't have this equation memorized. If I ever need to use it for something, I have to look it up. So you don't need to memorize the Stefan-Boltzmann law. But you should understand like what goes into it, right? You should understand it conceptually, even if you don't remember the numbers and you can't necessarily run the calculations. You should understand conceptually what we're talking about here. So the energy that's coming into the Earth, or the energy the Earth is absorbing, is a function of the insolation, which is represented by S in this equation, right? So the amount of sun energy that we're receiving, and A for albedo. So how much of that, what percentage of that energy is the Earth actually going to absorb versus just reflecting away? So that's the energy that we're getting in. And then our energy going out depends on the temperature. And we measure that in degrees Kelvin. So that's degrees above absolute zero, right? 0 Kelvin is absolute zero. But the size of a degree is the same in Kelvin. And since Celsius, we're just putting the zero at a different spot. So that the energy out is dependent on that temperature of the Earth, right? How much we're going to radiate out. And if we put these things into the equation, we can figure out, given what we know about the amount of insolation that the Earth is receiving and the average albedo of the Earth, run the calculations, that says the average temperature of the Earth should be negative 18 degrees Celsius. So when we convert from the Kelvin back into Celsius, we should get negative 18 degrees Celsius. And that's what the average temperature of the Earth should be according to the Stefan Boltzmann equation. But in reality, the average temperature of the Earth is more like 15 degrees Celsius. And so we are much warmer than the Stefan Boltzmann law tells us we should be. Now, the Stefan Boltzmann law is sort of a basic piece of physics. This equation is not wrong. So what this is telling us is something else is going on besides simply the Earth absorbing some percentage of the insolation and then heating up and re-radiating out radiation based on that. Something else is going on that is making the Earth's average temperature so much higher than what physics tells us it should be. And so what's going on here is that the Earth has an atmosphere. We have this envelope of air surrounding the Earth. And I've greatly exaggerated the size of the atmosphere in this diagram just so that we can see conceptually what's going on. So insolation comes in through the atmosphere. Our atmosphere is transparent to visible light. Right? Visible light's passing right through our atmosphere. Some of it gets reflected back out off the Earth, back through the atmosphere, back into space. Others of it is absorbed by the Earth, and the Earth re-radiates out infrared, longer wave radiation. But as that longer wave radiation is going through the atmosphere, some of that is going to get absorbed by the gases in the atmosphere. So some of the gases in our atmosphere are what we call greenhouse gases. They're going to absorb some of that outgoing infrared, longer wavelength radiation. And then just like the Earth, after they absorb radiation, then they re-radiate it out. And so some of it they're going to radiate out into space, but then some of it is going to radiate back down to the Earth. So now the Earth is receiving energy from two directions. We're receiving visible light insolation from the sun. We're also receiving this thermal infrared radiation being radiated back down from our own atmosphere. And so that's going to raise the surface temperature of the Earth. So the temperature here at the surface is going to end up higher because we're getting some of this energy essentially trapped in the system. It's not leaving back out into space. It's staying in circulation. And that is the greenhouse effect. So when we look at the gases that make up our atmosphere, if you remember our little pie chart there of what gases we have in the atmosphere, the two biggest ones that we have are oxygen and nitrogen. And these two gases are transparent to all forms of radiation. So shortwave insolation passes right through oxygen and nitrogen, isn't absorbed, doesn't reflect off of them, just comes right in. And then the longer wave radiation, the thermal infrared radiation, again, goes right back out through the oxygen and the nitrogen. So that's making up, 99% of our atmosphere, no effect on that radiation going in and out. But we have these gases that are present in very small percentages of our atmosphere that are greenhouse gases. So these are gases that are still transparent to that short wavelength visible light radiation, the insolation that's coming in from the sun. It passes right through those greenhouse gases, but they will absorb longer wavelength infrared radiation. So when energy goes back out, it's not going to pass right through these other gases. And these are gases like carbon dioxide, methane, nitrous oxide, or water vapor. these are gases that are going to absorb that longer wavelength radiation and then radiate some of it back down to the Earth. So they're going to absorb and re-radiate that energy. And the reason that these gases have that property, that they act as greenhouse gases, is because they're more complex molecules. So oxygen and nitrogen are very simple molecules. O2 is the primary form of oxygen that we find in our atmosphere. That's two atoms of oxygen stuck together. That's all it is. Same thing with nitrogen. It's primarily present in the form of N2, two atoms of nitrogen stuck together. It's a very simple molecule. But these others are a little more complex molecules. So CO2, carbon dioxide, is a carbon atom with two oxygens, kind of on either side in kind of a V shape. Methane, CH4, it's a carbon with four hydrogens around it. Nitrous oxide, it's an oxygen with two nitrogens attached to it. Water vapor, H2O, it's an oxygen with two hydrogens attached to it. So these are more complex molecules. They've got several different kinds of atoms. They're not perfectly symmetrical, and so that allows them to absorb that longer wavelength radiation and act as greenhouse gases. So this greenhouse effect is a natural process. There are amounts of these greenhouse gases naturally present in our atmosphere. And if there wasn't, again, we'd be negative 18 degrees Celsius on the Earth, and we wouldn't be here. It'd be too cold for us. So some degree of natural greenhouse effect is essential for life on Earth. The problem comes when human activity amplifies that greenhouse effect. When we put more of those gases into the atmosphere than were there previously, and so more of that outgoing radiation gets absorbed and re-radiated back down to the Earth, and that causes a warming of the Earth. So the two basic ways that human activity is altering the energy budget of the Earth are by changing the albedo of the Earth's surface and by adding greenhouse gases into the atmosphere that increase the amount of outgoing radiation that is trapped and isn't able to just pass through and leave the Earth. So here's what that looks like if we break it down by specific wavelengths. So what you see at the top is the incoming and outgoing radiation from the Earth. So in red is our solar radiation, and you can see that it's primarily in the visible portion of the electromagnetic spectrum at the short wavelength visible light. So we've got all of this solar energy coming in through our atmosphere, and then the Earth is radiating energy back out, and that's the blue. So it's radiating it back out in the infrared wavelengths, longer wavelengths. And if we focus on that outgoing, the blue section there, what we see is they have that nice blue line, that curve, that shows what the Earth should be radiating out. Then the jaggedy part inside that shows the actual amount of energy at each wavelength that is leaving the Earth. You can see the actual energy that's leaving is overall much less than what the Earth is producing, and that it's way less in particular wavelengths. So there's some wavelengths that a lot of energy is getting through, other wavelengths that almost nothing is getting through. And we can break that down by the different components of the atmosphere that are absorbing parts of that energy. So the next little bar down on that diagram, that's the total absorption of energy by different parts of our atmosphere. And then below that, those little, the narrower bands show the absorption for specific greenhouse gases. So the top one there is water vapor. So you can see that certain wavelengths, water vapor is going to absorb almost all of the energy coming through it. Other wavelengths it's going to let go through. Then carbon dioxide has different wavelengths at which it is trapping energy versus letting it through. Ozone, methane, nitrous oxide, right? They each have specific wavelengths of energy that they absorb. So specific bites they take out of the energy that the Earth is trying to radiate into the atmosphere. And this is actually one of the ways that astronomers are able to figure out the composition of the atmospheres of other planets, both in our solar system and increasingly planets we've discovered orbiting other stars. So we can get an idea of what's in their atmosphere by looking at what kind of radiation is actually escaping from that planet versus what isn't. And depending on the wavelengths, we might be able to tell, okay, there's got to be a lot of, say, carbon dioxide in that planet's atmosphere because the energy coming off of that planet is missing a chunk right at the wavelengths that we know that carbon dioxide absorbs and traps. So you can see how much of that Earth's radiation is not making it through the atmosphere, is getting grabbed by these greenhouse gases so that it never radiates out into space off of the Earth. And so all that stuff that's getting absorbed by these different gases is being radiated back down to the surface and increasing our surface temperature of the Earth. So there we were looking at what wavelengths each greenhouse gas is absorbing. We can also think about, well, how much warming are these going to actually produce? When we look at what energy is a specific gas going to hold in, how much is it going to actually warm the Earth? And so one way to look at that is to look at the global warming potential of different gases. So the global warming potential is how much warming is going to be caused by a gas as compared to the same mass of CO2. So CO2 is our benchmark. CO2 is our standard by which we measure the global warming potential of other gases. So the CO2 has a global warming potential of 1. And then other gases are going to have a number that represents how many times more global warming they contribute to than an equivalent mass of CO2. And this is measured typically over a 100-year time scale. So the global warming potential is going to be a function both of how much energy that gas is going to absorb when it's trying to pass through it, and how long that gas is going to stick around in the atmosphere. Because the atmospheric stock of carbon, in the case of the gases that are carbon-based molecules, or the various other molecules, right? They each have their own cycles, like the carbon cycle. That there's inflows into the atmosphere, including inflows created by people who are adding extra of these gases to the atmosphere. And then there's outflows. These are eventually going to leave the atmosphere. So we put some CO2 into the atmosphere, for example, it's eventually going to get reabsorbed back out of the atmosphere by photosynthesis or absorption into the ocean or various other things. Okay, so it's going to stick around for just a certain period of time. And so we're looking at a 100-year time scale to kind of equalize that with all of these different gases. So what you'll see from that chart is, again, CO2, we give it a global warming potential of 1. It's our benchmark. Then methane, another very common greenhouse gas, has a global warming potential of 28. So if we were to emit 1 ton of CO2 into the atmosphere right now and a 1 ton of methane, and then we were to look at how much the Earth warmed from each of those things over the course of 100 years, the methane would have warmed the Earth 28 times as much as that CO2 did. And then you see we've got some other gases that have even higher global warming potentials. Okay, so HFC 152A has 138. Nitrous oxide is 265 and goes all the way up to SF6 that has 23,000 times the amount of global warming potential on a kilogram for kilogram basis as compared to carbon dioxide. So carbon dioxide, as compared to other greenhouse gases, is a pretty weak one. So it sticks around for quite a while in our atmosphere as compared, like methane cycles out of the atmosphere more quickly than carbon dioxide, but CO2 absorbs less energy while it's in the atmosphere. So CO2 is a comparatively weak greenhouse gas as compared to some of these others. However, this is a kilogram for kilogram comparison. We're emitting way more CO2 than any of these other gases. We'd be in big trouble if we were putting out as much SF6 as we are CO2 because it's got such a much bigger global warming potential. But we're producing huge amounts of CO2 as compared to these other greenhouse gases. And so CO2 ends up coming out on top when we look at what's called radiative forcing. So radiative forcing is how much change in the Earth's energy balance is caused by a particular factor. So a thing that's happening, a thing that's changing about our climate system, how much does that change the amount of energy that the Earth is retaining? Okay, how much does it alter the Earth's energy balance? That is the radiative forcing contributed by that thing. So greenhouse gases are the source of some of our major radiative forcings. Right? They are things that alter the Earth's energy balance. And the radiative forcing of a greenhouse gas is going to depend on its global warming potential and its mass. So how much warming does 1 kilogram of this gas do, and how many kilograms of it have we put into the atmosphere over and above what would be there naturally? Okay, so you can see there on the chart that the radiative forcing from CO2, it's the top bar there, is much bigger than any other gas. So even though CO2 has a low global warming potential on a kilogram for kilogram basis, we're just putting out so much CO2 that it's making the biggest contribution to radiative forcing. It is increasing the amount of energy that's kept within the Earth and therefore the increased temperature of the Earth. So the bar shows our best estimate of the radiative forcing, and then the little whiskers around the end of the bar show our uncertainty range. Right? So all of these things, there's some degree of uncertainty. We don't have an exact number, but we have a best estimate and a little bit of range to it there. So CO2 has the biggest radiative forcing. Then you can see methane is the next one down. And so methane, despite being 28 times stronger in global warming potential, is contributing a little more than half of as much radiative forcing as CO2 is, because there's just less methane that we're putting out as compared to the CO2. Then we've got some of those other greenhouse gases there, again, making positive but smaller radiative forcing contributions. Then we have radiative forcings that involve changes in albedo. So there's 2 main classes of those. One is aerosols. So these are things that go into the atmosphere that primarily end up reflecting back solar radiation. So they're increasing the albedo of the Earth, making the Earth lighter colored. So those, you can see some of them listed there, and they have this negative radiative forcing, right? They're cooling the Earth. So things like mineral dust, sulfates, etc., they're cooling off the Earth. And again, there's a wide uncertainty range around it, but our best estimate is that they have a negative radiative forcing. They're cooling the Earth. And then albedo due to land use change, has actually a net cooling effect. So we get urban heat island effects in urban areas, but we have even bigger areas in rural areas where human activity is actually increasing the albedo and therefore creating a cooling effect. If you take a forest, which is a pretty dark colored thing, cut it down, replace it with, say, cattle pasture or cornfields, those are lighter colored, they have a higher albedo. So the net change, when we put it all together, add it all up, the positives and negatives, human activity changing land use, changing the albedo of the Earth's surface, actually creates a negative radiative forcing. It's a cooling effect on the Earth. So we can add all these things up to get the overall, the net radiative forcing. And despite the fact that there are some factors in here that are cooling the Earth, these aerosols, the albedo change from land use cover, the positive radiative forcings are much bigger. And so we have an overall warming effect on the Earth. So we're changing the Earth's energy budget to warm up the Earth, to increase our temperature by trapping more of that solar energy within the Earth system. You'll also notice on this chart, the last bar there, it says changes in solar irradiance. So that's a natural radiative forcing. So most of what's going on in the Earth is, at least within humans' timescales, pretty much in balance. We're not getting a radiative forcing, we're not changing the Earth's energy budget as a result of natural factors, but there are some small changes in the amount of energy we're getting from the sun. So the sun has been giving us a little more energy. But you can see that the size of that, the size of the radiative forcing from changes in the sun, a natural process, is minuscule compared to the size of the radiative forcings that are generated by human activity. by putting more CO2 and more methane into the atmosphere, by changing our land use, etc. Those are all much bigger than that tiny little natural change in radiative forcing from changes in the amount of solar radiation that we're getting. Okay, so that should give you the background you need to do your lab assignment for this week, where you're going to be using some simplified models of the Earth's energy system. So you're going to be able to play with different radiative forcings, different factors, different things that we're doing to the Earth, and see the effects of that on the temperature and the energy budget of the Earth, moving around things like greenhouse gases and albedo. So best of luck on that, and I will talk to you next week.